Hello everyone, welcome back. In this video, we'll be discussing about the last problem of today's weekly contest, maximum sum of subsequence with non-adjacent elements. The problem is actually very hard. Don't go by the number of accepted solutions. I would say more than 50 or 60% of solutions were not intended to be passed, but passed because of poor test cases or poor evaluation. Having said that, I would take you through the exact thought process that I had while solving this problem. One quick disclaimer is this problem will require understanding of segment trees. Even if you don't know about segment tree, that's fine. You will not be able to code the solution, but you should watch the core part of the problem where we have discussed how to think about recursion in general, right? So that is independent of segment trees because that will help in any recursive function you write in future. Having said that, there is a complete segment tree series that I have created in this channel. You can go through that series. You just need to go through first and second part of the series, and you should be good to code this solution as well. So with that, let's get started. The problem states that you are given array nums of positive integers, and you are also given 2D array queries where each query is position and a value. Now for every query I, the task is to set the value at that position in the array to the given value, and you have to calculate the answer for the query I. The answer would be the maximum sum of subsequence of nums where no two adjacent elements are selected. Now we will calculate the answer for every query I and finally return the sum of all the answers across all the queries. And since the answer can be large, you have to return it modulo 10 power 9 plus 7. So let's take an example. Let's say nums is 359. Now there are few queries, right? So let's take first query. First query says that change the value at position 1 to -2. And if you do that, the array would become 3 minus 2 9. Now what is the value at this query? The value would be the maximum subsequent sum when no two adjacent elements are selected. So in this case, 3 and 9 are not adjacent elements, and this is the maximum subsequent sum that you can get. So the value here is 12. Now let's talk about second query 0, -3, which says change the value at index 0 to -3. So the array would become -3 minus 2 9. And again, the value would be, you have to figure out the maximum subsequent sum where no two adjacent elements are considered. So in this case, the maximum subsequent sum would be 9. You would not want to take any of the negative values because that will decrease your sum in general. So the maximum sum possible is 9, and hence the value here is 9. So across the two queries, what is the total value? 12 plus 9, 21, and hence 21 is the answer. So hope the problem statement is clear. Now what is the brute force way to solve the problem? The brute force approach would be, let's take one query at a time, create the array, figure out what is the subsequent sum, and then again apply the second query, figure out what is the maximum subsequent sum according to the given criteria, and so on and so forth. So basically, after every query, we need to somehow figure out the maximum subsequent sum where no two adjacent elements are selected. So this problem in itself is a independent problem and actually a standard problem as well. So if you already know about the solution, feel free to skip the 5 to 10 minutes of the video where we discuss this particular problem. So the problem is, given an array, tell me what is the maximum subsequent sum of this array. For example, in this case, the maximum subsequent sum would be 2, 2, 8, 6. And one more condition given is no two adjacent elements should be selected. So that's why we haven't selected this 4, this 3, this 5, because they are adjacent to one of the selected elements already. So if you look at this, 4 plus 8, 12, 12 plus 6, 18. 18 is the maximum subsequent sum possible for this particular array. Now, how to calculate this value efficiently is the question. It's not always true that all the adjacent elements will be giving you the maximum value. Why? Because let's take one small example. Let's say this is 1, right? And in this case, you would want to, let's say you will take this, right? Now, instead of taking this, you can take this one and this one and this one, and this will yield you the value greater than what you will have if you take only the adjacent elements. Why? Because skipping some elements, you are able to select a sequence of elements that will give you a greater value than you would have gotten, right? So that's where the greedy approach would not work for sure. So you need to think of a way where you can explore all possible paths and give the optimal answer. So the obvious approach here is try to think of a recursive solution and then memorize it to get a linear time or a quadratic time solution using memorization or dynamic programming, right? So if you think about it, we need to figure out what is the maximum subsequent sum for this entire array, right? Now, in the final array, there are two possible choices. Either 0 would be there or 0 would not be there, right? These are the two possible choices for this first element itself. Now, if 0 is there, then you are sure that you will not take 1, because that's by definition you can't take adjacent elements. So if 0 is there, what you want what is the maximum subsequent sum for this remaining array. Isn't this problem exactly equals to the original problem? Original problem said that what is the maximum subsequent sum for this entire array. The reduced problem is what is the maximum subsequent sum for this reduced array. So hope you can see the recursion. Let's talk about the second path as well quickly, wherein you decided not to take the first element. In that case, your array is simply this, and again you want what is the maximum subsequent sum with this remaining array. So you are able to dissect the problem into smaller sub problem of its own type, which is basically recursion, right? So if you do this, let's say you define f of I. F of I denotes what is the maximum subsequent sum of the array starting at index I. So if this is index I, f of I would have like two different values. Either it would be either you will take index I or you will not take index I. These are two choices, right? And if you take index I, you will not be able to take index I plus 1, and you will want what is the maximum subsequent sum for this remaining array. So if you have taken index I, you have already taken array of I into your subarray, and you are saying that okay, now I will skip I plus 1 to give me the what is the maximum subsequent sum starting at index I plus 2, right? And if you don't take this index, you are saying that I am not taking I itself. So let's get rid of this. You are saying that I am not taking this I, and in that case you will say what is the maximum subsequent sum for this remaining array. So in simple words, you will say what is the maximum subsequent sum starting at index I plus 1, and whichever gives you the maximum, that will be your final answer, or that will be the maximum subsequent sum starting at index I. And once you have this recursion, you can simply figure out the value of 0, and that will be your final answer, right? So if you apply this recursion, this is the array we will get for this particular above array, right? Now I will not go into the driver and other things of this particular recursion, because that's the baseline, and if we go into that, it will make the video longer. So if you face difficulty in understanding that, I would encourage you to first solve easier DP problems before jumping to this problem itself. Okay, so we now know how to, like, if you code this entire thing by yourself, this will take you order and time. I will leave that as an exercise to you. If you are still not clear, you should write the recursive function itself and memorize it to understand why it is order n, right? Now we know how to find out maximum subsequent sum where adjacent elements are not equal, where adjacent elements are not taken in order n time. Now this problem you have to solve q number of times, because for every query you will have a different array, right? And for every array you will need to find the same thing, maximum subsequent sum with no two adjacent elements are selected. So if you do this entire thing naively, this will take you order q into n time, q number of queries. For each query you will have, you will change one of the indexes, that means the array is changed, and you will run the algorithm again, and that will take you order n time. So overall complexity is q into n. Now this should not pass ideally, because q is 5 into 10 power 4 and n is also 5 into 10 power 4. But this is what was passing for various Java solutions. So that makes the number of solution actually higher. But this is not intended solution for sure. Now, how to optimize this? So there are two ways, right? First, you say, okay, I know that I am just changing one index in one query. So can we somehow skip computing everything else and reuse whatever we have computed before? For example, let's say you are changing this particular index j in a particular query. You are changing, let's say, this to 5, right? Now, if you are doing this, you know all of these will remain same, right? F of j plus 1, j plus 2, j plus 3, j plus 4, like all of these will remain same. Why? Because they all depend on whatever is there after me, right? Now, but these may change, and if we can figure out a way to change these things efficiently, we will we can basically solve the problem efficiently, right? But the issue is there is no direct correlation, or rather there is no simple way to get direct correlation to figure out which all index will change and by how much, right? So if you take a look, this is one of the variation of this array itself, where we simply change this 8 to something else, in this particular case 1. And if you see this, all of these have changed, right? It was 18, it became 14. It was 16, it became 13. 14 to 12, 14 to 12. And notice the difference by which they have moved is not actually the difference of the original number and the new number. So original was 8, new is 1, difference is 7. And notice the difference between what has changed. So this became 14 from 8, so this moved by 6, which is not equal to 7. Again, this became 12 from 14, so this moved by 2, which is again not equal to 7, and so on and so forth. You will find similar examples afterwards. So overall, what we are saying is there is no direct correlation between what you are changing and what effect it will have on the rest of the elements, right? And also the fact that there is one fact that not only few indexes are changing, almost everything before j is changing, at least in this particular scenario, right? So there will be scenarios where everything before j will change, and if you do it naively, this will again take you order q into n time itself. So if we need to optimize this, we need to somehow think of a way to update one value and run this entire algorithm dynamically, such that the effect of the changed value propagates all the way through, and you should not be you should not actually do this one by one for every index, right? So that's basically the crux. Now, how to do this? One of the way to do this would be divide and conquer, or any range query data structure which uses that. So in other words, you just divide your problem into smaller problems, and there will be problems which will not change for at all. And if those problems doesn't change, you don't need to recalculate anything for those problems, right? So one simple thing would be, let's visualize this entire thing, the segment tree, with all these values at the root or the leaf of the trees, right? So all these values are the leaves: 2, 1, 2, 4, 8, 3, 6 and 5. Now you need to compute these values here, right? Now the value at these nodes would simply be what you want to compute ideally. For example, let's say if you want to do a range sum or a range product, these value would simply be the sum of whatever exists below. And similarly for range product, this value would be the product of everything that exists below. But in this scenario, what we want what is the maximum subsequent sum such that no two adjacent elements are selected finally. So that, like, every value, you might think, okay, I might want to store what is the maximum subsequent sum that exists for this subarray. Now if you do this, so in segment tree, like for those who know of segment tree, if you update any index, all of the nodes or all of the parents for that particular index will change. So all of these nodes will change, none of the other nodes will be affected. And if you are able to change these nodes efficiently, your job is done, right? So that's what exactly we need to solve for. So we need to solve for a way to figure out these values efficiently. Now what are these values? These values are simply some function of these two values only, right? And if we are able to merge two nodes efficiently, our job is done. We can simply update this node and forget about what other nodes have changed, and just this entire segment tree creation process or segment tree updation process will take care of updating all the nodes which should have been updated, right? So let's try to first figure out what is this merge function should be, right? So for example, we have considered two nodes, one 0 to 3, second 4 to 7, and we are trying to merge them to get a node which represent a range 0 to 7. In other words, we are taking these two nodes and merging them to create this node, right? Now I have simply expanded the values at this node for clarity, and this will be the new array. Now notice you can't iterate on this array for sure, because that will not be optimal. So without iterating over the array, you need to merge these two things to get your final answer. Now what you want, that actually depends on the problem. So in this particular case, we want what is the maximum subsequent sum with no two adjacent elements taken. So that, let's start with that. So we want, at this point, we want what is the maximum subsequent sum that is possible with no two adjacent elements taken. And to actually calculate this value here, you need to think of in a recursive function. So the next 10 minutes of the video, pay focus, because you need to understand how recursion works in general, right? So in this case, you want what is the maximum subsequent sum for the range 0 to 7. Now if you want this value here, let's call this m, maximum subsequent sum as m. If you want the value here, you can assume that you already have these two values here, right? Again, notice I've said assume, because that's how recursion works. If you are able to merge these two things, then this value is something you can compute from its children, and its children value you can compute from their children, and so on and so forth. So if you are able to merge this part efficiently, just one level efficiently, rest of the things will be taken care of by the recursion itself, right? Just to reiterate this part, what we are saying is, if we are able to determine how to merge two nodes, then we already know the value at the leaf nodes for each of them, right? So if you figure out what is the maximum subsequent sum at 0, 0, that's 2. maximum subsequence sum at 1, this one. So the leaf nodes you already know of. Now if you are able to merge these two, you know this value, you know this value, you know this and this. Now because you know this and this, you will know this. Because you know these two values, you will automatically know this value, and because you know these two values, you will automatically know this value, right? So that's how recursion works in general. If you want the value at this node, you can assume these two values, whatever value you want, that is computed for the child nodes, and with using that you want to compute the value at the parent. So in this particular example, we know that we'll assume that we know what is the maximum subsequence sum for the array 0 to 3 and what is the maximum subsequence sum for the array 4 to 7, and with that we want to calculate what is the maximum subsequence sum for the range 0 to 7. Now we want to merge these two values. Now you can't simply say the maximum subsequence sum from 0 to 7 would be ml plus mr. Why? Because this ml might have 4 as well, we don't know, and this mr might have 8 as well, very well possible. And if you simply sum them up, you are saying that whatever final array you will take 4 and 8 both, and that's the violation of the criteria itself. You can't take adjacent elements. So you need few more parameters. With just ml and mr, you can't figure out the value of m for sure. So what are those parameters you need? So first of all, you need to understand, okay, what is the maximum subsequence sum for this part. And if you, let's say, get this as x, so you can simply sum up x with mr, because that basically is safe, because you are sure that 4 is not taken. So whatever is the maximum value here, you can simply sum them up, and that is one possible candidate for answer, right? Now this candidate exists when 4 is not taken into consideration. Now second possibility could be, let's take 4. So second candidate would be this plus this. So what you want what is the maximum subsequence sum skipping the first element. Let's call this y, and one other candidate would be ml plus y, yml, because even though you have taken 4, that's fine, because you are not taking 8, you will not violate any of the criteria, right? So in total you want 3 different things. One, you want ml and mr for sure, right? So that's is max right and max left, right? Now other thing you want is, if you want to take this, you want to understand what is the maximum subsequence sum with just this, or in other words, skipping the last element, what is the maximum subsequence sum. So that's what you want. And in similar fashion, you want one more value, which is skipping the first element, what is the maximum subsequence sum, right? So these are the 3 things you want, and notice these things you want from different candidates. So from LHS, on the left part, you want 2 things: max value and what is the value if I skip the last element. From RHS, you want what is the max value and what is the value if I skip the first element. Now think about it, these 2 nodes are identical in every sense. That's what we discussed just a while ago. So if we want what is the value skipping the last element from LHS, that value we have to compute for this node as well, right? Skipping the last element, what is the maximum sequence sum. And similarly, we also need to compute the value for this, for the merged array as well. Why? Because we are expecting them to be present for the child array, and because that needs to be present, you need to have those values for this parent array as well, because those values will be utilized to merge this parent with some other node to get a final bigger value, right? So if you are expecting something from the child node, that something you need to compute for the parent node as well. So in total, you want three things. One is what is the max value, that's like what maximum subsequent sum, that is the goal, overall goal of ours. Now to calculate this, we discovered that we need two more things. What is the maximum subsequent sum skipping the last element? What is the maximum subsequent sum skipping the first element? And you need these three values for all the nodes, right? So now our goal has slightly changed. We want three things: max value skipping the what is the maximum subsequent sum skipping the last element, maximum subsequent sum skipping the first element. And again, just think about it recursively. You want these three values for the top, so you can assume that these three values are already calculated for all the children, and using that you can try to compute the value for the root. And if you remember, we already computed max value previously. That is simply max of L1 plus R3, which is max value and skipping the first element, and L2 plus R1, which is skipping the last element from the left and max value from the right. So we already know how to compute max val from these things. Now we want to compute skipping the last element, what is the maximum subsequent sum, which in turn means you don't want to take this element into account. You just want to say what is the maximum subsequent sum for this range. In other words, what is the maximum subsequent sum with no two adjacent elements considered in the range 0 to 6, right? Now you want to avoid the last element, which in turn means you want to avoid this part, this element fully, which in turn also means that you can use this value for sure, skipping the last element. So you can say, okay, I have R2 that denotes what is the maximum subsequent sum if I skip the last element, right? Now, can you sum up this R2 with L1 or L3? The answer is no. Why? Because this R2 just says that I have skipped the last element, but this R2 doesn't say anything about whether 8 was there or not, right? This is exactly the same issue which we faced previously, and that's why we introduced these two things, right? We want to merge these two things, and we want to merge such that the criteria that is given in the problem is not violated. So if we want to merge, we need to understand whether 8 was taken or not, and if 8 is taken, you should not take 4, and if 8 is not taken, you are free to choose 4 or not, like that's your choice. So in this case, you have R2, which says what is the maximum subsequent sum if you skip 5, but you can't sum up R2 with L1 or L3, and if you sum up R2 with L2, you will get a valid value for sure. Like you can say this is a valid candidate for what is the maximum subsequent sum. You are saying that whatever is the maximum subsequent sum here, you are simply avoiding this at all and saying what is the maximum subsequent sum here. So if you combine these two, that will never violate the condition. But will it be the maximum subsequent sum of the merged array? The answer is maybe or maybe not, right? Why? Because there might be a case where you have taken this and not taken this, and you got a maximum subsequent sum, right? And this scenario will never be covered with L2 and R2. So that's where you need two more variables. Again, this is exactly analogous to what we just discussed a few minutes back for the original problem, and that's the reason we introduced these two things. So we need two more variables now. First variable is what is the maximum subsequent sum if I skip this and take this. What is the maximum subsequent sum if I skip this and skip this, and based on that I can choose one of the values here to get the maximum value, maximum subsequent sum. So if I just expand this, we now need two more things, which is the maximum subsequent sum skipping the last element that we already had, but with the condition that first element was also skipped. And similarly, maximum subsequent sum, skipping the last element with the condition that the first element was taken, right? Now, if we have these two values for all the nodes, again, why all the nodes? Because we we are computing this value at root, and we want these two things from the children. So because all the nodes are identical, we want these two things for all the nodes, right? So we'll come there again. So for now, we are saying that to compute this value, you will need these two variables. Why? Because let's say this let's call this r4 and let's call this r5. Now once you have r4, you know that r4 says that first is not taken. Now if first is not taken, you can simply merge r4 with l1, because whatever is the maximum subsequent sum here, you can simply use that, because if first element is not taken, whatever you do here, whether 4 is there or not, it doesn't matter, the condition will not be validated because 8 is not there. So this will be one possible candidate for our answer, right? Another possible candidate would be r5 plus, again for r5 what you're saying is you are skipping the first element, last element, but you are taking the first element into account, right? And if you're doing so, you don't have the authority to take this element at all, and that's what, and you need what is the maximum subsequent sum from the remaining element, and that's what L2 gives you. So you can simply sum this up with L2, and this is another possible candidate. So this, if you take max of these two, you will get the value of skip last element, right? Now notice we started with finding out max val, we ended up introducing two new variables. Now we started figuring out the value of first variable, and we ended up introducing two more variables, right? What it means, it indirectly means that you need to compute those two variables as well for all the nodes and for the root as well, which you are trying to compute for. So you need to compute these two values as well for the root node, and you can assume that these two values are already there for all its children, right? Now how long to continue might be a question for some of you, and that is a valid question, but we'll answer that in a bit. So let's first try to compute skip first element. What it means we want to skip the first element and figure out what is the maximum subsequent sum for this remaining array 1 to 7. Now if you take skip first element, you can surely utilize L3, which says what is the maximum subsequent sum from this array. That's L3. Now will L3 be enough? The answer is no. This is again very analogous to the previous part, so I would encourage you to pause and try to move forward if you can. So to figure out the maximum subsequent sum for everything except the first element, you have to break down L3 in two parts again. Why? Because L3 may have 4 or may not have 4, and based on that you will decide what to choose from the right side, right? So in the very similar fashion, you will need two more variables, which is skip first take last and skip first skip last. In other words, you are saying that if I skip first and take last, then what is the maximum subsequent sum? Let's call this L6, right? And whatever is the L6, you can simply take skip first element with this to get your final answer, right? Now this is one possible candidate for skip first element. Now what is other possible candidate? Other possible candidate would be, okay, I don't want to take 4 at all, right? And I will take whatever is best for me on the right. So if I don't take 4, I have the liberty to either take this or not take this. So in simple words, I can simply use R1, which basically says what is the maximum subsequent sum across this element, which includes both the criteria as well. So if I call this L7, so another possible candidate would be L7 plus R1, and based on which one is maximum, that will be the value of skip first element, right? Now again, you have done something like not so obvious. Basically, you were trying to compute something here and you ended up introducing two more new things, right? And which means that you need to compute these two new things again for the newer set of for the parent as well. Now this chain can continue, and that's where you need to pause and try to understand if you are going in the right direction. So you need to converge all of these to a fixed set of numbers. Like this can't go on up till infinity. So what is that fixed set? And if you look closely here, you just need 4 values. Why? I would strongly encourage you to pause and try to think at least 15 minutes for yourself. So if you look at this value, or let's look at this value, skip last element. What does this mean? This means that what is the maximum subsequent sum if I skip this element? In other words, what is the maximum subsequent sum for 0 to 6? Now, for 0 to 6, the maximum subsequent sum can either include this or may not include this. Right? These are the two choices for the first element, and you already have like skip first, and you can actually compute take first as well, right? And based on, if you have these two values, right, take first and skip first, like this is actually these two values itself, take first and skip first. So if you have these two values, you can just take maximum across these two values to get this value, right? In the similar fashion, if you want to compute skip first element, which is what is the maximum subsequent sum if I want to skip this element, that is simply what is the maximum subsequent sum if I skip this element, and what is the maximum subsequent sum if I take this element. If I take maximum across these two things, you will get this complete value. Now I know this might not sound very intuitive, but it actually is if you try to pause and think by yourself, because this is exactly equals to what we have started with. So if you remember, we started with a very basic recursion where we said what is the maximum subsequent sum for this entire array, and here what we have said that there are only two possible cases: either you will take this element or you will not take this element, and based on that you can decide what is the maximum subsequent sum. So if you already know what is the value if you take this element, what is the value if you don't take this element, you can simply take maximum across these two to get the final value of f of I, right? That's what we discussed, and that's exactly what's happening here. So if you look back again, what we are saying is, if you have maximum subsequent sum for this entire array, where, or let's talk about the other part first. So let's say you want skip last element value. In other words, you want this maximum subsequent sum where this thing is not there. Now you already have two different things. First, maximum subsequent sum where this element is present, and maximum subsequent sum where this element is not present. And if you just take maximum across these two things, you will get the final value, right? What I'm talking about is we just simply need 4 different things: skip first, skip last, skip first, take last, take first, skip last, and take first, take last. You can arrange these things into a 2D array with 0 and 1, and first will be the one axis and last will be the other axis, and this will denote skip first, skip last. This denotes take first, skip last. This denotes skip first and take last, and this denotes take first and take last. Now we have these 4 values. Let's say now let's try to compute what is the maximum subsequent sum for this value, right? You assume that you have all the 4 values for all the children. Now you want to compute this value. Now how will you compute that? The answer is what you need. You want to not have first and you want to not have last. In other words, you are saying that you don't want this and you don't want this. So now you want what is the maximum subsequent sum across this array, right? So what you can say is, okay, what is the maximum subsequent sum if I take 4 and don't take 8? What is that? The answer would be you are taking 4 and skipping this. So skipping first and taking last. Skipping first and taking last. So you already know this value, right? Let's call this R10, right? And you are saying you want a maximum subsequent sum where you don't take 8 and you don't take last one as well. So you want this one. Okay, let's call this L10 and let's call this R00, right? So this is one possible candidates, L10 plus R00, for combining these two array, right? Another possible candidate would be where you say, okay, I will not take this but will take this. In other words, you are saying that you don't take first and last for the first from the left part, which is L00, and you take first and skip last from the right part, which is take first and skip last, which is R01. So based on whether L00 plus R01 is greater or L10 and R00 plus R00 is greater, you will take that as the value of your final content where you don't want first and last. In the similar fashion, when you take other elements, you will be able to get one of the combinations. And if you can enumerate all the combinations, which is very easy, for each combination you will have to take max across two different elements. You can simply figure out all the 4 values. And now once you have all the 4 values, what you wanted in the beginning, the max value, right, which simply is what is the maximum subsequent sum across this entire array. Now that, remember the first choice where you are saying that what is the maximum subsequent sum if I don't take this. Let's forget about this for now. So if I don't take this, what is the maximum subsequent sum of this entire array, and if I take this, what is the maximum subsequent sum of this entire array? And you have both the values, so you can simply take max across both the values to get the answer. Now what is the maximum subsequent sum if I take this, which basically says I want to take the first element, which is this part. Now what is the maximum subsequent sum? You can simply take max across these two to get that value. Now other cases when I don't take this, which is this particular column. So you want what is the maximum subsequent sum if I don't take this. That you can get by simply doing max across these two elements and get what is the maximum subsequent sum if I don't take this. So if you take this, this is the maximum subsequent sum. If you don't take this, this is the maximum subsequent sum. You can take maximum across these two to get the final value. In other words, you can take the maximum across this entire matrix to get the final maximum subsequent sum across this entire array, right? So in essence, you just need these 4 values, and these 4 values can be computed based on only these 4 values from the children, right? So that's the entire thought process that you should have while solving these kind of problems. Now I know this is a bit tricky, so just rewind and watch the entire process again. We haven't done anything magic here. We simply started by saying that we want maximum subsequent sum for each of these nodes, and once we started figuring out what is the maximum subsequent sum, we got to know that okay, we need, like, with just maximum subsequent sum from the children we can't compute maximum subsequent sum of the parent. We need few helper variables or helper values as well, and that's where we introduced 2 new helper values for the children's. Now once we started computing the value for the helper values, because those needs to be computed as well, we realized that we need 2 more helper values. And once we started computing the the value for other helper values, we realized we need more variables. Now finally, after looking at this, you should, like, after you have done this exercise one more time, let's say you want to figure out this value as well, and you are doing that same exercise, you will notice that this value you can compute from whatever you have already have, and that's where you will realize that okay, you actually don't need all the values, you can simply work with these 4 values and just take maximum across 2 different things based on what you're computing, right? Now either you can say that okay, answer of 0 0 would simply be max of left of 0 0 plus right of 0 1, comma left of 1 0 plus right of 0 0, and similarly you will get some expression for this, this and this. Or you can do it in a slightly smarter fashion by saying that okay, I want this value, right, which means this should be, this should not be there and this should not be there, but I don't have any condition on this part, right? So there are 2 possible choices, either it will be there or it will not be there. So let me run a loop for 0 and 1. So I don't want this and I don't want this, so this is 0, this is 0. Now either I want this or I don't want this, and if I want this, I'm sure that I don't want this, and if I don't want this, I'm sure that I can afford this. So you can simply take L01 with R00 and L00 with R10, exactly what we discussed, and this part you can simply do with a for loop. Now you can simply run a for loop with 0 and 1 and figure out the value here, and based on, because you know the left and right for both left and right, you can simply take the maximum. So the pseudo code for that would simply look like this. Let's say you want to calculate answer of ij for each of these. For each of these you will iterate over k, which is 0 and 1, which basically denotes what is the state for this element, whether you want to take this or you don't want to take this. Now based on what is the state of this element, you can easily decide what is the state of the next element, and based on that you can take what you want to take from the right and take maximum across all of those to get the final answer, right? So this is the very simple merge function for your current problem. We had gone through all of this and this is what you got, and this is exactly what you see in most of the codes as well that you might see in the solution section. And believe me, this is the thought process that you should go through to get this thing. Now it doesn't mean that I have done all this size while solving the problem. It's just that with practice you will get to understand okay, for doing this I want these 2 things, let's try to compute this, and while doing this you will say all of these. So these things will come with practice, but you have to go through this in some way or the other, right? Now finally we know what is the merge function. Now we know the merge function, we can build a segment tree, right? So this is how a segment tree would look like. The base case would simply be everything is 0 except this particular column, which is I want to take the left one and the right one. Why? Because this is just a array of one element, which is 2. Now if you are saying that I don't want first one, like this will say I don't want first one and last one, which is simply saying that I don't want this 2 at all. So 0 is the maximum subsequence sum you can get. This says I don't want the last one, but I want the first one, which again means that you don't want 2, right? Even if you want the first one, that is not possible because you don't want the last one, right? So again the maximum subsequence sum is 0. Similarly for this will be 0. Now here it says that I want the first one and the last one, and hence I want 2 in general, so you will simply take 2 here. In the same fashion you will compute all the values for all the leaves and then apply this simple for loop to get the values for all of these nodes. Now when update comes, okay, what is the answer? First of all, for this array, answer would simply be the max across all these 4 elements, right? Now when update comes, let's say update comes for updating this 8 to 1, right? So we'll simply come here and update this 8 to 1, and while merging, all of these things will be taken care of and everything will come to a stable state. And once you have everything in stable state, you can again take maximum across all these 4 elements to get what is the maximum subsequence sum across this entire array, and that would be correct. So what is the overall time complexity of this algorithm? First of all, you are building this entire segment tree. Building this entire segment tree for this initial array would take order n time multiplied by like you have n nodes, right? So it will be multiplied by what you are doing in to build each of the node. First of all, you need to fill 4 integers. So you have to, like, if you talk about the leaf node, you are simply filling everything with 0 except 1 1, which is 2. So you're doing like order 4 operations, which is constant, right? Now after that, for merging, what you're doing, you are simply doing a 3 inner loop variables, but the loop itself goes over only 2 times. So overall 8 operations here. So in total you are doing 12 n operations approximately to build this entire segment tree. Now this 12n is very small. It is in the order of n, and n is actually very, like, n is small and it should be small because you need to iterate over all the elements at least once. So this is acceptable. Now what about updates or queries? So during queries, what you're doing is you are coming and updating this, and similarly you will merge these two things to get this. You will merge these two things to get this, and you will merge these two things to get this. In other words, you will be updating log n number of nodes, just like any other segment tree updates, point updates. So you will be merging log n number of times, and we have already seen that each merge take 8 operations. So you will take order 8 log n operation to merge this entire thing, and this is also fine. Basically this you will be taking this operation q number of times. So overall complexity is 8 q log n multiplied by a very small constant factor, which is 8, and this will pass the given time constraint. Now here comes the sad part about this problem. The problem was very well set. I would say this is a very good problem to strengthen your understanding about how recursion works in general and how you should think about the states you want to preserve in segment trees. But when I code this entire thing in C++, it says that everything is passed but time limit exceeded. So if I just open this here, it says all is passed but it took too long, which is actually sad, because this problem was this solution was of the order q into 8 log n plus 12n, which is way better than what n square solutions was accepted in the contest. So I would say if you are able to get to the state, just forget about getting accepted. If you are able to code the entire thing and get it at least up to 500 test case to ensure that your solution is working, and after that if it's getting TLE, that's fine. You don't need to worry about optimizing that, right? So next we're looking at the code, but if you have watched till this point and you understood this, or at least you think you understood some part of this, this is the right time to pause and try to code this entire thing by yourself, because once you start coding you will realize there might be certain things which you still don't understand, and that's where you will come back again and rewatch that particular section to understand, to strengthen your understanding about that area, or watch for or ask follow-up questions in comment if required. So next we're looking at the code, and I assume that you have at least tried this at least once, right? So the code is like exactly what we discussed, nothing different. We will simply build a segment tree. We'll come to how to build a segment tree again in a minute. We'll go over all the queries, we'll update the particular index with the particular value, and then we'll query the tree for 0 to n-1. This is like nothing but saying that X is the first node of the tree, which is the root node, because that will have whatever you want. and after that we'll simply go over all the 4 values to get the final result and add back result to the answer and finally return answer modulus mod. Now you might have to do it again here as well in some scenarios, but in this case the values are too small to exceed the 64-bit integer, so this was fine. Coming back to segment tree, there are 3 functions here: update, query, and build. Build will simply build the segment tree for the initial time for the given vector, and query update will just simply update the position with this particular value, and query, as the name suggests, it will query in a particular range. This function is not needed for like fully. I just coded this just to show you guys that you can indeed now answer what is the maximum subsequent sum in a range x to y, not only in the entire array but in a particular range, which is very powerful if you think about it. So that's why I just coded this function. We'll come to that. Now let's go to the build. This is the constructor just create an array of size 4, array of nodes. What is node? Node is simply a 2D vector of size 2 cross 2, right? Now once you have this 2D vector allocated for every node, you will build the tree. Building the tree is simply going over all the nodes. For the leaf node, you know that val of 1 is v of l, others would be 0, which is actually assigned in the constructor itself. Now once you have populated the leaf node, for all other nodes you will simply merge the 2 nodes from the left and right. Now how to merge? Merge function is exactly what we discussed. We will simply do a 3 loop and figure out the value of the current node at the current position left comma right by taking what would be the possible options for the last element of the left side, right? So after this merge, we'll have all the nodes built for segment tree. So this entire thing is now built at least one time. Now once update comes, you will simply go and update. Once you reach the leaf part, you will simply go and update the leaf node value. After that, you will, this is the usual part, you will either go left or right based on where your target position lies. And once you have updated that, you need to update the current node as well, because if you have updated this part, this node might have changed as well. So that you need to update based on again merging the left and right. So this is the update part. Query is standard part. We again does the exact same thing. The neutralization value is a bit tricky here. You want a node, or you want a 2D array which will not affect any other things. So let's say you are merging these two nodes, or you only want this node as an output if there is only one node and this node is not there. So you need to merge 2 nodes, right? That's what you know. So if this node doesn't exist, or if you don't want to take 4,4, you need to return something that will neutralize, or that will not interfere with whatever value this will return, right? So that's the neutralizing value. In case of range sum, it is 0. In case of range minimum, it's int max or something like that, because if you take min of int max comma something, that something will be the output. So that something will not be affected by what we are returning with a node which is not existing, right? So in this case, if you see, we are returning an empty node, which simply means everything is 0, 0, 0. Now why that works, I would leave that as an exercise for you. So this is it for this video. If you have any doubts, feel free to post them in the comment section below. I would be happy to answer. If you like the video, give it a thumbs up and do subscribe if you haven't already. I will see you in the next one. Okay, one last thing. I think yesterday's biweekly contest as well, that has a segment tree problem as well, and that can be solved in similar fashion again. So would encourage you to give it a try. Again, this is not this problem at least can be solved in other ways as well, which doesn't involve, or which can involve segmentary state in different ways. But one of the ways where segmentary state will be modeled is same as what we discussed today. You want a block of size x, or you want to answer for a query of block of size x, you can simply try to keep how many blocks are present in a particular range and try to back calculate for calculating how many of them are present for a particular node, what would I want, and based on that again go on computing this, and you will realize that we don't want more than 2 or 3 values here. So that should be it. I am not making a video for this. Based on the interest on this video, I will decide whether to make the video on that as well or not. But if you need any help, I'm more than happy to answer that in the comment section below, or to guide you in the right direction if you have actually watched this particular video and understand this. So with that, we'll end here, and I will see you in next week. Thank you.